So we're doing chapter 6 right now. The next chapter after that is chapter 8. Then seniors leave. Then we're doing chapter 11 and 12 with the juniors. So.
Wait, so we just have this in chapter 8?
Seniors, yeah. If you're junior, you got 2 more after that, which is like solid, because that means every single test is worth less in the long run. Cool.
But
cool.
chapter 8, how's that?
It's vectors.
When do we take our final?
The week of the 10th. Alright. I mean, I'm not gonna lie to you. I haven't gone through it in depth right now. In chapter 8 in depth right now. I've been like focused on chapter 6, which you'll see with some of the comments I'm making today. So I'm really doing everything I can to make sure you like not just pass the chapter 6 test, but like be successful in it. So you guys, your full-time job right now is to be a student, which means everything you do in this class should be like benefiting yourself, right? So take away the distraction. Put that phone away. If someone is like distracting you, like tell them politely, like stop. You know, like I want to pass this class. If you are a junior, think about where you'll be in a year and a half. The answer is not living with your parents. I'm hoping. Like hopefully you're in college, which means you're gonna have to be self-aware, in charge of yourself. Right? There's not going to be anyone sitting there micromanaging you. Like, oh, hey, quit talking. Oh, put away your laptop, blah, blah, blah. Like, you got to, like, focus yourself, you know? Right. So I'm gonna present everything as simple as I can. It's, like, clear. I have things marked so, like, certain examples go with certain homework problems. And, like, you know, it's a give and go. I want you guys to work on being like active students, right? Meaning, like think. Don't just be a bobblehead, taking down notes, but like actively like think about, does it make sense? Do I have questions? Like take initiative and like earn the grade you want, right? Like get the grade you want. It should be a good chapter. Here's a hint. So Alex is due every week. Why don't you pick matrices as the 5 topics to do this week? What a thought. It would help you prepare for the chapter test. You would get better at it. Man, okay. These thoughts I have, like, wow. You know?
Wow.
So, because matrices, this is what we're doing. Might as well do it on Alex, and then it's extra practice. Okay, so just looking at the lesson plan, today we should be able to finish 0.6. Like, we're on it. Let's do it. We're going to finish it. I don't think we'll have too much trouble. How many of you guys have seen matrices before, whether it's Alex or previous class? Like, I'm just curious. Okay. This is about what the other period was. It's about like half and half. Who's in AP Computer Science right now? Okay. Or have taken it? Yeah. So that means like there's at least one other person in the room that like knows about arrays and you know, rows and columns and figuring out like where I am. Okay. So if you have questions, like you don't just have to ask me, you can like ask your classmates if they know what they're doing. Tomorrow we'll be doing 6.1, Wednesday 6.2. Let's see. Yeah, so by Friday, I'm hoping we're done with the lessons by Friday, so we're gonna have like 2 days of reviewing, but I've built in an extra day because pretty sure 6.1 will take 2 days. Okay, so now that administration stuff is out, let's get going. I'm hoping we understand this. All right, so matrix operations. So you've probably seen the movie The Matrix. No, yeah. It's all right. I know it's older than you are. But
interesting. Blue pill.
Yeah, blue pill, red pill, matrices. Okay, so if you ever see like the numbers flashing up, it's like showing a matrix, which is like this like row and column. It's like a square with all these numbers and like stuff falling. And if you've never seen the movie, you're probably like, what the heck? So a matrix is a rectangular array. So it's a rectangle full of rows and columns of numbers. It's arranged rows and columns enclosed in brackets. Each value in the matrix is called the element. So, and then the dimensions of the matrix with m rows and n columns is denoted by m, x, n, right? So you say it as m by x. So for instance, this first matrix, which is matrix A, I can talk about the dimensions So it is 3 rows because each row, like each level is a row, and then each up and down line is a column. So we actually have, so it's m rows by n columns. So this first dimension, I would say it is 3 by 4. So that's your first example. This is a 3 by 4 matrix. And if I want to call in a specific element, I can label it as AMN, meaning A, which row am I in? So this is row, column. How would I label this 3 right here? How would I like locate it? It's kind of like an XY coordinate, like where I am. So right now I could say I am, you know, the 4th room back, the 3rd room to the right. So whatever, right? So it's like your XY coordinate. How do I specify this 3? Like what are its coordinates? Where is it located? Which row, which column?
Row 2, column 2.
Row 2, column, row 2. So this is row 2, column 2. So this is A22. That's how I would say its location is 3, right? So 3's location is A22. Row 2, column 2.
I don't get that. Can you explain that?
Yeah, so we're gonna do another example. If I asked you to locate A14, what is located at A14? Okay, so first step, the 1 is your row. So your first row is the top row, right? First row, the 1 row is your top row. And then I'm looking at 4, right? So 4 is your column, looking at the 4th column. So which number is in the crosshairs, right? 6. All right, so now we've done an example like where I tell you the location, you find the number, and we did a number, and we sold its location. Let's do the example. We're going to be working with this over and over again. Let's do another one. Let's do another one just to make sure we're okay. Yeah. So do one more. Let's say, what is the location of -8? How would I write the location for -8? All right, what's its location?
Row 3, column 2.
So A32, because it's row 3, column 2, so it's row 32, or it's A32. Because it goes row, then column, row, then column. Okay, so we can go through the first example. Example 1, use this matrix A, right? 4, 5, 7, -1, 3, -8. What are the dimensions of A? So think about this. So it's M by N. M is the number of rows. N is the number of columns. So this is 2 by 3 because it's 2 rows. It's like a level of cake. Like your rows are your levels of cakes, right? Have you seen like a multi-tier cake?
Of course.
Like a, right, all on top of each other? Yeah, so how many layers you have is how many rows you have. Okay. And then if you're standing in line at a bank, because they only have one teller open, you're like in a column. There's like 4 people in front of you. Like 4 people vertically. Okay, so let's see. Oh, here it's only 3 columns. And then we want to find the value of A23. Okay. So row 2 is this one. Column 3. So which one's in my crosshairs? -8. Okay. Yep. So just so you know, example 1 is similar to the homework problems 1 and 3. So if you have questions on homework, hey, look at this example. All right.
Cool.
Yeah. Now we're going to go through matrices with special names. We're also going to practice like the dimensions, telling the dimensions of a matrix. All right, matrices with special names. So let's first go to the row matrix. Surprise, surprise. Literally a row matrix is just a matrix with 1 row. What are the dimensions of my row matrix? Exactly, 1 by 4. 1 row, 4 columns. What about a column matrix? Surprise, it's a matrix with 1 column. That's why it's called a column matrix.
2 by 1.
2 by 1, because it's 2 rows, 1 column. So if I say blah, blah, blah row matrix, it's just going to be 1 row. Blah, blah, blah column matrix, just 1 column. Columns are vertical. Rows are horizontal. So I'm talking about a single row. It's like, it's the, third layer of your cake or whatever. Like it's that whole layer. And then I can distinguish between rows because it's between the layers. Like, okay, whatever. I'm just trying to get visual. Square matrix. The square matrix has the same number of rows and columns. So, it's 2 by 2. So a square matrix can be 2 by 2, 3 by 3, 4 by 4, 5 by 5, 18 by 18. Literally, the rows and columns have to be the exact same number. A zero matrix is a matrix in which every element is 0. Literally, there's no numbers, just zeros. That's it. What are the dimensions of this one? 2 by 3. 2 rows, 3 columns. I think we're getting the hang of it, maybe a little bit. And then identity matrix. I'm going to highlight it. I'm going to write important because this is the one we're going to use probably the most. This is important. So the identity matrix is where every element on the main diagonal is 1. So the main diagonal is this one. This is the main diagonal. And then we know this is a 3 by 3 matrix. So guess what? This is a square matrix, but it's also an identity matrix. So it can be more than one type. Yeah. And then there's one last thing I want to talk about, which is equal matrices. Forgot to write this on the packet. Okay. Equal matrices are where each element of one matrix is equal to the corresponding element in another matrix.
Like they're the same exact thing, the whole entire thing, or just like they have corresponding parts?
Exactly. Each part that corresponds is the same, which means the overall thing is the same.
Can you give an example?
Yeah, since I'm done writing the, corresponding element in another matrix. Let me make sure I wrote every word. Alright, so equal matrices, each element of one matrix is equal to the corresponding element in another matrix. And this also means they have the same dimensions. Alright, so an example of this would be if I have matrix A, which is 1, 2, 3, 4. And then I have matrix B, 1, 2, 3, 4. So I look at every single element. If I look at the first elements, right? The let's see, A11, B11. I'm telling the location in my matrix, right? So B11 is the first row, first column of my B matrix. So check it out. Those are the same. If I look at the second element, right? So, A12, B12, those are the same. Right, so you notice like, oh, corresponding parts are the same. Which means, overall, I can say matrix A is equal to matrix B. Because they all have the same things. Okay. If it's not the same number, then it won't be equal. Because matrices, each element has to be equal to the corresponding element. So if I went back and I changed this, oops. Let me say this was like a 5 instead. Uh-oh. Then I can't say they're equal because they're not the same. Alright. So far, okay, how do you feel? Questions? Let's break it down. Okay, cool. Alright, so matrix operations. Matrices can only be added or subtracted if they have the same dimensions. Uh-oh, only if they have the same dimensions. Only can add or subtract matrices if they have the same dimensions. Okay. So if you add two matrices, you're just going to be adding the corresponding parts. Right? So the top left corner, you add to the top left corner.
What if it's two different dimensions?
You can't add them then. You only can add or subtract matrices if they have the exact same dimensions. So I'm adding the row 1, column 1 of each matrix together. I add the row 1, column 2 of each matrix together. I add the row 2, column 1 of each matrix together. Feel like you guys are getting the point. Exactly. And then I make a new matrix. Actually add them together. Guess what? Subtraction is very similar. I'm going to take A's top left corner and subtract B's top left corner for a new value in a new matrix.
Wait, I don't see that.
See?
We start like row 1, column 1, 2.
An example?
Yeah, like
That'd be better.
So when you did row 1, column 1, you like
A minus E equals, or I'm sorry, A plus E is literally A plus E. If I take the
But I thought when you do row 1, column
row 1 column, nope, that's multiplying. When you're multiplying, you go like this. That's when you're multiplying matrices. We're just adding. So literally, it's almost like you're overlapping them and adding the ones where they have in the same space. That's not really good English. But I tried color coding it so you can kind of see, like, each location you're adding all the things that are there. Tall. Good morning. Sit up, please. All right. Subtracting. It's the same thing. Yeah. So it's better to go through an example. I feel like you'd understand a little better. Just so you know, example 2 is like the homework problems number 11 and 13. All right. So let's find each of the following. Here's matrix A, B, and C. Let's go through and let's write the dimensions. That's a good practice. What are the dimensions of A?
2 by 2.
How about B?
2, 2.
C?
2, 1.
No, yeah.
Yep, 2 rows, 1 column. All right, so what is, if I want to do matrix addition, what's A plus C? Ooh, I hear a lot of like, no, can't do it, no solution, blah, blah, blah. Aha. Ooh, Maya, good job. Say it again. Okay, what's that have to do with anything?
Well, you just can't do it.
Exactly, it's not possible because they have different dimensions. Because you're taking a 2 by 2 matrix and trying to combine it with a 2 by 1, you cannot do that.
So you would just say not possible.
Yeah, not possible. Different dimensions. Cannot do that. Okay, so let's do B minus A.
Well, after you use the factor, I think you just put like A, B, or B
Where?
as the answer.
For number A?
Like that's the CS of B minus A.
Oh, okay, I'm going to do that example now.
Okay.
Alright, so I'm going to do B minus A. So let me write matrix B. 10, negative 2, negative 3, 16. Now I'm going to be subtracting matrix A. 2, 5, negative 1, 3. So I'm going to go step by step. So I'm going to take 10 and subtract 2. Then I'm going to take the negative 2 and subtract 5. So I'm going in order, right? So I'm taking, the first row, second column of B, and then I'm subtracting the first row, second column of A. It's like the corresponding locations, the corresponding places. What's another way to say this? What's another way to explain this? Huh? Yeah, it's this locations. It's the locations are the same.
Coordinates.
Yeah.
Alpha.
Negative 2 minus 5. So this one, the negative 3 and negative 1 are at the same location in the matrix. So when I'm subtracting one matrix from the other, like they're at the same place, I'm going to subtract them. I don't know another way to say this. Negative 3 minus 1, and then here I have 16 minus 3. So I'm trying to like circle and show you as I go. All right, let's actually do the computation. Where? Oh yeah, I forgot the subtraction sign here. So 10 minus 2 is 8. Negative 2 minus 7. I'm sorry, negative 2 minus 5 is negative 7. Give away the answer. 3 minus negative 1. 3 plus 1 is just negative 3 plus 1 is negative 2. 16 minus 3 is 13. And then that's it. That is the solution. That is the answer. It's that matrix. Let's see. Example 3 is like homework problem number 20. So scalar multiplication. It's possible to multiply a matrix by a constant called a scalar. So if you're in physics, you know scalar just means plain number. It doesn't have direction. It's just a number. So I can go through. It doesn't have a variable associated with it. I can take that number, distribute it to every single part of my matrix. So it's literally you're just doing distribution. Taking negative 3 and multiplying it by every single thing in the matrix.
What are matrices used for?
Ooh, that's a good one. Cool, I'll give you a real life example. So my undergraduate thesis, I did astronomy research, which means basically I'm taking pictures of the night sky over and over again. I don't think you know how your phone works, like a DSLR camera. Do you guys know how it works? No. So literally, imagine a bucket that collects rain, right? Okay, now imagine that you have 1,000 buckets by 1,000 buckets. That's literally what a DSLR is. It's a bunch of buckets, but instead of collecting water, they collect photons, which are packets of light. So I literally have a matrix. I have 1,000 numbers this way, 1,000 numbers. It's 1,000 by 1,000 numbers, this giant matrix. And each one tells me how many photons it collected by a certain number, a certain brightness. Cool, so, you know, I took hundreds of photos of the night sky using this telescope and the, you know, CCD imaging. It's literally like on the back of your phone. Like, if you look into it, like it's little, almost like an LED panel, something like that. Literally collecting these photons. So what I did was I used matrices. I got data from it. It told me how much light was coming in. And sometimes the buckets would be too full, they would spill over. So photons would spill over. It's one example. Cameras. Every single one of your phones has a camera in it. And they all use this technology with matrices. Yeah, that was a good one. Yeah. What's really fun is when you're trying to go through 2,000 photos that are, it's like, there are 1 million pixels. So it's like each photo.
How many photons make up a pixel?
It just depends. But how many like buckets make up a pixel? How many like collecting? Well, if you have like a 4K screen, it's 4,000 pixels per inch. Like, you know, ultra def, whatever. So imagine having like thousands of numbers across of columns, thousands and thousands of rows, and going through and trying to like see the difference within each one. And then you have a 3D matrix, because then you have the one photo with all the different numbers, but then you have all the photos you took that night, as well as all the photos you took every other observation night.
What does that do for you? Why do you care how many, just to see the change?
Proving a variable star, proving the period of a variable star, proving that these exoplanets have transits, planets, like proving these stars have exoplanets because the brightness of the star will decrease. Yeah. Okay, let's keep going. So let's distribute the negative 3. All right.
And this technology, you can take the picture and turn that into, you can then like.
Yeah, your phone does that all the time.
Dude.
Your phone does it all the time.
And it can have technology to convert a picture and then one of the metaphorical buckets into a number, which is a piece of the matrix.
Yeah. Yep.
That's cool.
Yep. So there's a language called MATLAB. It's kind of like, almost like Java, but MATLAB is literally matrix laboratory. You feed in and do all this matrix calculation stuff. Anyway.
Sorry. Every time I do the problem, I'm supposed to put it in like a matrix format. So you want to know. Okay.
Yep. All right. Let's keep going. How are you feeling so far? We just have like one more page of notes, like more questions.
Did you give you homework also?
Yes, I'll give you some time. That way you can ask questions to each other and we can help you. All right, properties of matrix operations. So you look at this and you're like, there's a lot of words, there's a lot of letters, I don't know what's going on. Trick play is just algebra 1 all over again. So remember algebra 1, the commutative property? Yeah, algebra 1. No, okay, that's fine. If I take 1 plus 3, isn't that the same thing as 3 plus 1?
Yes.
Okay, so if I take matrix A and add to matrix B, would it give me the same thing if I did matrix B plus A? Doesn't matter the order you added in, you still get the same answer. That is the commutative property. Doesn't matter the order you added in, you still get the same thing. If I add 1 plus 3, same thing if I added 3 plus 1. The order for addition doesn't matter. Associative property of addition. Okay, what if I took like 2 plus 4 plus 6? Just a moment. Okay, if I added 2 plus 4 and then added 6, does that give me the same thing if I added 4 plus 6 first and then added 2? Yeah, so if I add these two matrices first and then add the third one, it's the same thing if I added the first and the third one and then the second. Like, doesn't matter the order you add, you still get the same answer. Doesn't matter the order you add, you'll still get the same answer. Okay, addition, we're fine. Distributive property, if you have the scalar in front of the parentheses when you're adding or after, it's still the same thing. You can just, instead of taking the scalar, like, instead of adding the two matrices and then multiplying them all by the scalar, you can do the scalar first to both matrices and then add them. It doesn't really matter. Get the same answer. Yeah, so that's all it is. That's all it means. Like, we got this. Okay. So, example 4, find 3 times a minus b. So what this means is, I'm literally going to take a minus b and then multiply the result by 3. Order of operations. We're going to do the parentheses first, take matrix A, subtract matrix B. Alright, so this is just like your homework problems 25 and 27. Yeah, if we finish early, I'll just project the book and then we can get going on homework. Example 4, find 3 times a minus b. So 3 times, okay, so a minus b. A minus b. So that's 5 minus 1, negative 2 minus 0, negative 1 minus negative 2. Do we understand where these numbers are coming from? Like, if you don't understand this, I really, really want you to understand now. Because this is like the foundation. If you understand today, you'll be successful the rest of the chapter. If you don't understand today, it's going to be really, really rough for you. Because this is the stuff I have to assume you know in order for us to get to the meat. Huh? No, I'm not quite done. 0 minus 3, 3 minus negative 1, 2 minus 6. Five minus 1 is 4. 2, 1. What's wrong?
My water level is dinging.
I dropped my water bottle too many times. The surface, the top of it's like,
What is that? Cold.
I don't know. I just bought it and it's water.
Is it water or is it like a drink?
I thought it was coconut water. Imagine my surprise when I opened it and it's just water.
It's really expensive water.
Yeah, I thought I was getting coconut water with vitamins. All right, let's finish this out. What do I get?
Picture you think it's water and it's coconut water.
I hate coconut water.
Whatever. Distribute the 3 to every single part of your matrix.
Oh, this sucks.
Oops. It's not too bad. It's not too bad. As long as you are going step by step, it's not too bad. It's fine.
I just scanned. Do you want to just scan?
Who are you talking sass to?
She was talking fast to Dylan.
I don't know, but it is.
To Dylan? Oh, okay.
Oh.
What, you know what you're doing?
Oh man. What?
Huh? Yeah.
Just throwing something out, just tossing something in the bucket.
Okay, so now this is, oh my gosh.
I got this, and now I
Okay, are you ready? Are you ready for like the key to do we understand? Shh. Stop talking. Stop talking. Stop talking. Remember like 30 minutes ago when I talked about you have to take initiative to be a self-learner? Literally, I will not give you time in class to work on homework if you're just jacking around. Like, focus. Let's focus. Right? Let's learn the lesson. Let's go through the stuff together. Because I want you to be successful, but I can't want things that you don't. I can't want you to get an A in my class and then you bomb the test. That has nothing to do with me. All right? We need to focus, work together. Let's do this problem. I heard some people like, I don't know, I understand the rest of the lesson, but not this, I don't know. Okay, cool. So we're going to do it together. Let's do an example. So example 5 is just like homework problems number 33 and 41. Okay? So, solving matrix equations. So you can solve equations involving matrices using algebra. We're using the same algebra, okay? But instead of having a single number at the end for what x is standing for, instead, our x is going to be a matrix. Our answer is going to be a matrix. That's why it's a capital, large X, not just a small x. Okay. So how would I get the x by itself in this example? So the first step, get x by itself, and then like solve for the matrix.
So it's b plus a over 2.
B plus a over 2. Okay, so how did you go about doing that?
I added a to the other side and then divided by 2.
Alright, so I have 2x minus a equals b. First step to solve is get x by itself. Add a on both sides. I have 2x is equal to a plus b. Does it matter if I have b plus a? No. Commutative property. Commutative property. Commutative. I can add a to b or b to a. Does not matter.
Why is the x so big?
Because it's not just a single variable. It is a whole matrix. It's a capital X because it's a whole matrix. So if I get x by itself, I have x is equal to 1/2 of a plus b. Wait, does this look like our last example? Can you do 1/2 times the addition of a plus b? Can you do that? Yeah, of course you can. We just did one like it.
That's k.
Huh? What k?
Now you divide every number in that new matrix by 2.
Well, right. So let's go step by step. Here we go. Okay, so x is equal to 1/2. Negative 1 plus 5.
Oh, I get it. 2 and 0.
Okay, so let's keep going. Negative 1 plus 5, 2 plus 0, negative 1 minus 1. What? Adam, Noah? 2 minus 6, 3 plus 7. That way people can't complain when I don't have a screencast up. Like, oh look, here it is. You have to suffer through all 50 minutes, but there you go. Whatever. What? Yes. Yes?
But you have someone like me in your class that has to stop.
Well, don't do that to yourself. You're fine.
Thanks.
Okay, so I added them. Now I have to go through, multiply every single one by 1/2. 2, 1, negative 1, 4, negative 2, 5. Check it out. This is my answer, and it's a matrix. A matrix. Distribute the half to every single. Distribute the half to every single part of the matrix. Any other questions? So we should be able to pound out, at least have the homework the next 20 minutes. Like, imagine if you like focused this much every class, how much easier it would be. Oh my god. Okay. All right, no questions. We can do homework.